Okay, so let me start. So yes, so let me talk about eddy currents first. Okay, that we have discussed last time. Just check, guys, if you are comfortable with eddy currents or not, because there are few points that I need to tell you. Then we can proceed. Okay, so see, I was talking about eddy currents. Okay, the example I gave you was, suppose if I have a conductor. Okay, which I'm taking in bulk now. That means it is not a wire right now, but it's a whole piece of conductor, very big piece of conductor. Okay. So if I do that, if I take a piece of conductor or bulk piece of conductor, this conductor, right, since I'm calling it conductor, right, it's going to have electrons, the free electrons. They are right now rotating in random directions, all in random directions. Okay. So when I bring a magnet, I told you, let's say I'm bringing a north pole closer to this metal piece, right? The moment I bring the magnet closer to this metal piece, the flux through this metal piece is going to change. Okay, whether I bring the magnet closer or farther, right? The flux is going to increase. Right now it is going to increase, but if I take the magnet further, the flux is going to decrease. Okay, and what we already know from your Faraday's law is that amount of induced EMF is directly proportional to the rate of change of flux. That means induced EMF will be developed, induced current will be developed. Okay, so I'll show you now what will happen to the behavior of electrons because of this north pole being coming towards this magnetic, not magnetic, this metal piece. Okay, so just check. So you know, as the north pole is brought closer and closer, right, the induced EMF that will set up because of the change of flux will resist the incoming of this north pole. Okay, that means the metal piece, right, it has to develop some kind of north pole to oppose this incoming of north pole, right? In order to develop this, there will be a current induced in the anti-clockwise direction. Okay, and this current is what is known as eddy current for us. Okay, now what happens is, because of this, is that the electrons, they start rotating clockwise right now, giving us current in the anti-clockwise direction. That happens throughout the body of this conductor. Okay, so right now you can see the electrons are rotating, and the electrons, when they rotate, right, okay, they are going to keep on giving us current in individual sections or parts of this whole metal piece. That current, I told you last time also, we call it eddy currents. Okay, to give you another example, if I have a metal piece, and if I am taking again your north pole and south pole, but this time let's say I'm taking the magnet away, no? So when I take the magnet away, we are decreasing the flux, but still there's a change of flux. So the metal piece is going to respond, right? It's going to develop a induced current, and it doesn't want the north pole to go away, right? So it's going to develop a south pole here. That means the current that is going to be induced throughout the body of this conductor, right, is going to be a clockwise current. Okay, this clockwise current, again, we have to call it eddy currents. The difference is very simple. The difference is that we are not talking about current induced in a coil. If you're talking about current induced in a coil, right, we simply are talking about induced current in a coil or a circuit. But right now we are talking about induced current being developed in the whole body of a conductor. Okay, and one very important point which I told you last time was this: see, because of this eddy currents, what happens is this: see, the electrons are going to rotate, and they keep on rotating in this path. So they are going to keep on rotating in this path. Okay, and when the electrons, they keep on rotating this path, they hit other atoms and other electrons in this path. And when they keep on colliding, right, when they keep on moving in this path, right, they keep on colliding, they are going to generate a lot of heat. And when I say heat, right, it's a form of energy. And what is going to happen is that whole metal piece, right, is going to become hotter and hotter. Okay, now one important thing that I need to show you right now, an experiment, and I think it's going to make sense. Just check. Okay, so if I have a north pole here, suppose, and if I have a south pole right now placed like that. Okay, don't worry about with my diagram right now. These are the two pole pieces. Okay, my diagram has become very bad, but no problem. These are two pole pieces of a magnet. Suppose I have a pendulum. Okay, where I'm not going to suspend a bob, but let's say I'm suspending a whole metal piece. This metal piece can go back and forth in this magnetic field. Okay, so suppose if this metal piece, okay, is coming, I'm telling you again, if this metal piece is coming and entering this magnetic field, I'm just swinging it. Okay, using just like a pendulum is going to swing, it's going to enter the magnetic field. As this metal piece, it's not a coil here, okay, it's a whole piece of metal. I'm telling you again, it's a piece of metal. As it enters the magnetic field, what will happen? Is going to the one of the face, right, this face is going to feel the south pole, the other face is going to feel the north pole, more and more south pole and more and more north pole. Okay, so as this metal piece is going to swing and enter inside the magnetic field, this induced EMF will be developed in this metal piece, that let's say it's a copper right now. I'll show you in a video also in a while. Okay, I'll give you a link, you just check that. I think it will be you'll be comfortable. So when you see that this copper piece is falling, right, is falling and entering inside this magnetic field, this copper plate will become slower and slower. Why it is going to become slower? Because as the metal piece is entering the magnetic field, the induced EMF will be developed in such a way that it will not allow it to fall in this magnetic field. It will stop the motion. Okay, let's say it will oppose the motion. Okay, and as the copper plate is moving away from the magnetic field, right, again induced EMF will be generated and it will try to stop moving away of this copper plate. So in any case, if the copper plate is falling in this magnetic field, it will be, velocity will be reduced. And even if the copper plate is trying to go away from this magnetic field, even that time the magnetic field will not allow, okay, the induced EMF will be generated and the copper plate will not be allowed to go away from this magnetic field. Okay, so in any case, the motion is retarded, or let's say the motion is opposed. Okay, that's why last time, if you remember, I said something like this. Okay, eddy currents also follows Lenz's law. That means they oppose the cause of their production, or let's say they oppose the motion of the conductor in a magnetic field. Okay, so please remember that eddy currents, when they are generated, they always oppose the motion of a conductor in a magnetic field. Okay, because of which I told you one very important application of a eddy currents. Okay, so let me just show you very quickly, then we'll proceed. So see, I told you we have a train. We have train, and then I'm telling you that this train, right, this train wheels are made of metal. They are made of conductor. I have a track. This is a track of the train, and I want the train to stop here. If I want to stop the train here, right, the speed of the train must decrease. Okay, so as the velocity of the wheels are there, right, they are rotating right now. What I'll simply need to do is that I put here magnets. Okay, maybe I'll put here north pole, north pole, north pole, like that. And the other end, right, the other end of the track, which is will be somewhere else, will be south pole. Okay, so what will automatically happen is that as the wheels, okay, as the wheels are trying to rotate and enter into the field, right, the rotation of this wheel will be retarded. Okay, because the wheels are made of metal, and in the metal, eddy currents will be generated and their motion will be retarded. Okay, example, this is a wheel, it's trying to rotate. Okay, let me just show you that very quickly. I hope you're getting some idea at least. So if this is a wheel of the train, and suppose this is a north pole, right, automatically you will see that another north pole will be generated in the wheel, right, because of eddy currents. Okay, and this north pole will be opposed, right, its motion will be opposed. Okay, as it's trying to go towards north and north more and more, this will become north pole, and this north pole on the tracks, right, which is a real magnet, will oppose this wheels which is approaching this track. Okay, so it's going to slow down the train. Okay, so we call it electromagnetic braking also. So that's an example, that's an application of eddy currents. No, in electromagnetic braking systems we use that. Okay, it's important that we generate. Okay, now let me tell you what's disadvantage. Okay, the disadvantage of eddy currents is this. See, eddy disadvantage. When I give you the note, I think this point you just have to study. I'll tell you the questions also very quickly. Then I think everything should be fine. Okay, so just check. The disadvantage of eddy currents is that eddy currents, I told you earlier also, they produce heat. They produce heat on the metal surface, on the metal body, wherever they are generated. Okay, so example, I'll give you why this heat is bad. Transformer, I think you do not know what is a transformer. Let me just quickly tell you what is a transformer. Okay, we have this.
So I do.
Okay, you know, very good. Okay, so this is some core. We wind up some, let's say, wires. Yes, this is a core. Okay, we wind up some wires here. We wind up some wires here
Which type,
in a
sir?
transport. Huh? Any type. Let it be step up transformer,
So
step
which
down
type of transformer?
any type transformer. Okay, step up transformer, step down transformer. I'm not talking about Optimus Prime and Bumblebee. Okay, not talking about
Oh,
them.
sir.
Okay,
So I got
yes.
confused, sir.
You
Yes,
are
I
going
thought
to
that's
get me.
okay, sir.
If you were near me now, I would have punched you, I think, 10 times already. Okay, Christian?
Yes, sir.
10 punches to sure. Okay, from my side. Okay, whatever it is. So see, you will notice that in a transformer, just let's take it very quickly because later we are going to discuss transformer properly. As the current, okay, it's a real current here. This I capital is a real current. This current is a changing current. Changing current, okay. A changing current will produce changing magnetic flux. A change in magnetic flux mutually will induce some EMF on the other coil. So you will notice in the body of this transformer, the core of this transformer, okay, this is the core, which is a metal piece actually, okay. And we have this core because we want the flux to be linked more here. So don't worry about this, but the point is that whenever the current, right, this current is changing in this coil, you are also going to generate eddy currents in the core, okay. So let me just draw that eddy currents. You're going to do that. You're going to generate eddy currents, okay. As a result, transformer will slowly become very heated up, no. So it means there's a loss of energy because some of the electrical energy is being converted into heat energy. So there's a loss of power, or let's say loss of energy, right? So that is the disadvantage of your eddy currents right now, okay. So let me tell you what are the questions they can basically ask. So I'll just do that. And I'll show you how to minimize eddy currents. I'll do that. Let me just write the first question. The first question is, what are eddy currents? Let me tell you what are eddy currents very quickly. The currents which are set up in the body of a metal piece or a conductor, right? Because of a change of magnetic flux, we will call them eddy currents. And basically they are circular in nature, right? Spiral in nature, okay. Number two question is, what is the disadvantage of eddy currents, right? The disadvantage of eddy currents is what? The disadvantage is that they produce a lot of heat in the body of a metal, okay. So that's a disadvantage because it's a loss of energy. Then I'm going to tell you that what is the advantage, right? Or let's say what is the application. Application I showed you just now, you can use it for electromagnetic braking systems. I told you that. So that's one advantage. You can read more. I can give you in a note. I'm just going a bit fast right now. Number four is how to minimize. Suppose I want to minimize eddy currents, because you see they produce a lot of heat, right? So if I can minimize eddy currents, automatically the heat produced will be less. So I want to do that, okay. So let me just tell you what do we do. See, suppose I take a metal plate. This is a metal body, right? And what I do, I cut them into pieces, okay. I don't take a full metal body. Suppose I need a metal body, but I don't want to produce eddy currents. I'll take the same metal body but cut them into slabs like that, pieces, one by one, okay. Next to each other, we can keep it like that. It's the same metal body I'm taking, okay, from top and this one, right? They are same. This and this are same, except for the fact that you can see there are gaps now, right? I still have this metal body, but right now I'm having these gaps, okay, very small gaps, very tiny gaps, no. So we call this process as we call it what? We call it slicing. Also, we can call it. That's not the word, okay. We take smaller areas right now. Let me tell you how does it help. See, if you remember, the eddy currents are generated like this. They have to electrons have to rotate and they have to make a full circle like that, right? They're rotating, right? The moment I have this slicing, right, of this whole metal plate, see what will happen. This electron which was rotating in this path earlier now cannot rotate because we have sliced it and there's no path anymore left out. No, see, the electron wants to complete this path, but see, it is cut off, right? This whole piece is cut off like that. Even this electron which wants to complete this path is cut off, right? So these electrons, they do not find its way to complete this whole circular path because you're slicing into thin sheets also, we call it, okay. So we have a metal plate, but we have divided the whole metal plate into what? Into thin sheets. The moment you do that, you're cutting the area, okay. And when the area reduces, reduces, heat generation also will be reduced. I hope you understand my point, okay. So heat generation also automatically, you'll see it is reduced because the electrons, they do not find a proper path to travel, right? Okay, they cannot complete their path, so they cannot give us eddy currents anymore, no. So they're going to give less value of eddy currents, okay. So one way of minimizing eddy currents is what? You simply take a metal piece and divide and cut them, okay, or slice them into thin sheets. The moment you do that, the path of the electrons for which they are going to travel will be cut off. And if the electrons, the path is cut off, you're automatically going to reduce eddy currents, okay. So far so good. I think you are clear. These are the questions they're going to be asked. I'm going to give you in a note so you can study that also, okay. So I think this part is clear, right? Guys, can I start? Should I start your AC chapter? Is it okay? If you say okay, I will start. Anything you want to ask, you can talk about that before I start alternating current.
सर नोट्स
Yes, yes.
कब मिलेगा?
नोट्स मिलेगा कल, मिलेगा कल,
सर
कल मिलेगा, ठीक
सर
है।
क्या बजे सर बताएं?
कितना बजे मिलेगा? आई विल टेल यू Most probably maybe 2 or 3. I'm not sure right now, huh? So just I will inform you in the group. Okay, okay.
Yes, sir.
Okay, okay. 2 or 3, huh? Okay. Yes, yes. You can come on Tuesday also, but of course you have to let me know the timings and all. No? Okay. So guys. Okay. By the way, I'm using the new iPad, huh? So I got it yesterday. Yes, yes.
Congratulations, sir.
Yes. Now my whole pocket is khali. Okay. So those who have not paid the fees, please pay the fees. Okay. Otherwise, I'm pura kangal right now. Okay. Okay. So, okay. Let's proceed. So, is it okay? Can I start your alternating current, guys? Is it fine? If you have nothing to ask, then I'll proceed. Okay. Anybody wants to ask anything, you can ask. I'll wait for 10 seconds. If nobody's asking, I'm going to proceed. Okay. Okay. Thank you, Freddy. Freddy also paid the fees last time. That's why I think I could buy this iPad. It's very nice, you know. You can record. By the way, I'm not using right now. Uh, okay, just 1 second. Okay. Hello, hi, Arja. Hello, Arja. Can you hear me? One second. Okay, just give me 1 second. Till then, if you have any doubts or anything you want to clarify, you can ask me. This boy is calling me. I need to talk to him very quickly. Bio project. Okay, I have no idea. Give me 1 minute, guys. Okay, then I'll start this properly. Let's not be in a hurry, but we'll do it properly. Okay, in that 1 minute, you can take a break. Okay, then come back. Okay, we'll start alternating current properly. Okay, Arja, hello. Hello, Arja. Can you hear me? Hello. Hello. My network is so bad, Ray. Arja, can you message me in WhatsApp? Okay, I think you can hear me. Okay, 1 second. Hello, Arja, can you hear me? Acha. Tomorrow who will come? Who will come tomorrow? Your friends? Surajit will come, no, I think. Okay, okay. So I'll do like this. Okay, you ask Surajit to message me tonight. Okay, because I'm going to tell him what time to come near health complex. No, around maybe 11. I will pick him. Okay, but please ask him to give me a message, Surajit. Huh? Okay, ठीक है. Okay. Most probably 11 o'clock. Huh? Okay, fine. Okay, so I was saying something. Okay, let's start. Okay, then alternating current. We'll do it properly. I will discuss in detail. Okay. Now, your job will be to understand the basic parts and simple parts, and numericals are going to become not very difficult, but we have to understand very simple and basic parts from alternating current. Okay. If you're having doubts or any confusion, you need to ask me right now. Okay. You cannot proceed with the doubts. Okay. So let's start. See. Now, automatically. Okay. Let me just tell you what is a DC first. Let me show you what's a DC. A DC represents means direct current, and a DC source. Let me just show you. Okay, a DC source is simply your pencil battery. A pencil battery has a positive end. You know it has a negative end. The moment I connect it to a circuit, connecting a circuit means connect to a bulb or maybe radio if you want to play or anything, right? We're simply going to connect it one end positive like that, one end negative like that, right? Okay, and then the current. Let me tell you. If I tell you this point is A, if I tell you this point is B, the current will always flow from positive end of the conductor towards the negative end of the conductor, or let's say from positive of the battery to the negative end of the battery, right? That means the current will always flow from A to B. No chance current will always flow from A to B. no chance that current will flow from B to A. That is not going to be possible. Okay, so that's your direct current. Okay, so this is your direct current. Let me tell you what will be an AC. An AC is something, okay, or let's say an AC source. Your sockets, by the way, okay, the home, right, the sockets that you have, not like this, right? Okay, now in your sockets, okay, do you realize they have not written anything like positive or negative? Let me tell you why. There's no positive, there's no negative. You connect your charger this way, it will be useful. Of course, you connect it ulta also. Okay, I'm not showing you ulta, but let's say you're connecting ulta. Okay, left to right and right to left, or whatever, right? Doesn't matter. Okay, you connect it straight, it works. You connect it opposite way, any way you want. Okay, it still works, right? There's no positive and negative. Let me tell you what happens in a AC now. Okay, so this source, right, which I'm calling it AC source, we represent it like this. We draw a circle and we draw a sinusoidal curve inside it. Okay, this is how we represent an AC. There's no plus, there's no minus, because if this is plus and this is minus for the time being, after some time automatically you will see this will become minus and this will become plus. AC is going to alternate the polarity. Okay, but obviously in a battery, in a pencil battery, you cannot expect the positive to become negative and the negative to become positive, right? There's no change of polarity in a pencil battery. Okay, that's why the direction of the current also doesn't change, whether in AC, whereas in AC the polarity is going to change. Okay, you saw this socket will become, this point will become plus minus at the beginning, let's say, but after some time this will become minus and this will become positive. That means there are both ways the current can flow. Okay, the current can also go from A to B. If I connect this bulb now, see, I take this bulb, connect it like this, the current can go from A to B, no problem. And the current after some time can also go from where to where? B to A, right? So that's a property of AC. Okay, so let me just show you now how do we represent an AC mathematically and in a graph, and then you tell me whether things are okay or not. Okay, but AC is something which changes the direction. That's the first part. Okay, so now let me proceed. Okay, so see, now suppose I simply draw a circuit. Okay, I'm just taking a resistance right now. This is a simple resistor, and I'm taking a source. All of you know what is a source right now, so I'm drawing it like this. It's an AC source, you can already understand. I'm going to call E as the voltage of this AC source. Okay, and then I'm going to tell you that right now the current I've drawn from A to B, you can check. There's the current I, I'm calling it. Okay, so I is the current, E is the source or voltage of this AC right now. Okay, let me draw a graph and explain to you what is happening. I think the things will become much better now. Just check, give me some time, guys. Okay, to set up everything, and you should if you have doubts you can ask me. Okay, so see now, suppose I tell you this is time axis. This is time axis. This is the zero of the time axis. That means the time right now is zero. And this one I'm telling you is the current axis. The current axis tells me what is the value of the current. Okay, and let me tell you, I can even go down here. If I tell you this is positive current, this is taken to be as negative current. I'll tell you the difference between positive and negative current. Okay, give me 1 minute. So this is negative current. See, so this is time equal to 0. Let's say in this picture right now, the time is 0 seconds, and I'm telling you that the current right now is also 0. So our graph is going to start from here. The time is 0 and even the current is 0. Okay, then I tell you that after 1 second I see that the current has become 5 amperes. Just an example. So this is a time axis. The time axis will have 1 second of current, 1 second of time, 2 seconds of time, 3 seconds of time, and 4 seconds of time. Okay, just an example. So let's say exactly after 1 second, I see that the current has become 5 amperes. It has definitely rise. Okay, so let's say this is the value of 5 amperes. I am telling you that after 1 second, the current has become 5 amperes. So this is a point in this graph. Okay, then I'm telling you that the current that is flowing right now is flowing from A to B. From 0 seconds till 5 seconds, I'm telling you the current is flowing from A to B, and I'm telling you that this current is increasing, because you can understand initially the current was 0, now the current is 5 amperes and it is increasing. Okay, but the rate of increase of this current is not constant. That means the current is not rising linearly like this. Okay, so let me just remove that. I'm telling you at the beginning the current rises very fast, but after some time I'm telling you that the current has risen and become maximum of 5 amperes, but it is not rising very quickly after that. Okay, it is constant right now. Okay, not constant, but let's say it is rise to 5 amperes. Okay, but till 5 amperes the current is rising. Okay, let me tell you now what happens, not 5 seconds, sorry, after 1 second, no. Let me tell you what happens between the time of 1 second and 2 seconds. That means in between the time of 1 second and 2 second, okay. If you understand right now, the time is 0 seconds. When it reaches here, the time is 1 second. Between 0 second and 1 second, the current is rising and the current is flowing from A towards B, okay. That means the polarity, I can tell you, this must be plus and this must be minus right now, no? Okay. Now let me tell you what is happening, okay. Suppose I tell you now, the current is still flowing from A to B. The polarity here is still plus, the polarity here is still minus. But I'm telling you that right now the current starts decreasing now, okay. And in 2 seconds, let me tell you, the current was I equal to 5 amperes at 1 second exactly. But when the time is 2 seconds, I am telling you that the current is again becoming 0 amperes. That means the current is falling, okay. Let me show you a graph for that. And let me tell you again, I'll give you a reason why the graph is not a straight line, okay. So just give me some time for that. But let me tell you, the graph is falling down like a curve, no? In exactly 2 seconds, you can understand the current has become 0. Let me tell you what has happened in these 2 seconds, okay. The current is moving from A to B in these 2 seconds. In the 1 second, in those 1 second out of 2 seconds, the current was rising from 0 to 1, 2, 3, 4, 5. Okay, it has reached 5 amperes. And after that 1 second, between the 1 second and the 2 seconds, the current is falling. The current is falling and it is becoming 0. Okay. So in these 2 seconds, I can still tell you the polarity here is plus, the polarity here is minus, but the polarity values, right? The value of this EMF is changing, because of which the current is also decreasing. Okay, it is increasing first and then decreasing. Okay, we say that the AC, the current has completed half of the cycle. Right now, if this is happening, right, the current is increasing once, becoming maximum, and is again falling to 0, right? We say that the AC has completed half cycle. Half cycle, please remember this, okay? Don't worry, it is easy, you can understand. Then now after 2 seconds, let me say, between the time of 2 seconds to, let's say, another 1 second, that is your time, till 3 seconds. When the time was 2 seconds, you can already see the current I is 0. In the next 1 second, I'm saying that the current is again rising, okay? In the next 1 second, that means still 3 seconds, let me tell you the current is again rising, okay? The current is becoming again 5 amperes, but I'm writing a minus 5. I'll tell you the meaning now, and I think you will get me, okay? That means I have to draw a graph somewhere at minus 5 amperes. 2 seconds means this is the, yeah, between 3 seconds, it has rise to this much. So let me just show you the graph. The graph is again like this, okay? What I'm trying to tell you right now is that after those 2 seconds, the polarity has changed. Later, I'll show you how we can achieve this, okay? How can the polarity change and everything I'll show you. But for the time being, just remember the polarity will change. And this NB, the negative and the positive N, the B will become now positive N. And the A, let's say, has become now negative N, okay? Automatically, you will see between the time of t equals to 2 seconds and t equals to 3 seconds, the current now will start flowing from where to where? From B towards A, okay? Not from A to B anymore, but it will flow from B to A. That's why in the graph, you will notice I'm going to use the negative portion, right? Okay, the fourth quadrant you can check, okay? That means the current is simply, if this represents current is flowing from A to B, then this graph, right, represents current flowing from B towards A, okay? So right now in 3 seconds, I'm telling you that the current has become maximum right now, okay? Now again, what is going to happen? Once the current has become maximum, that means it cannot exceed more than that. You will notice the current will still flow from B towards A, for the time between 3 seconds and 4 seconds. But this, between this 3 seconds and 4 seconds, the current is going to fall to 0 again. So again, right, this is happening. Simply remember that current is flowing from A to B, because A is at positive polarity, negative polarity, right? This is the picture for 2 seconds. And in this 2 seconds, what is happening? Current is rising for 1 second and again falling for 1 second, okay? And it's becoming 0. Then I'm telling you that for the next 2 seconds, the current, the polarity of B becomes positive. The polarity of A becomes negative. Let me just show you that very quickly. Okay, now the current is not flowing from A to B. The current is flowing from B to A. From B, because B has become positive and A has become negative, okay? And in those 2 seconds, right, in the next 2 seconds again, the current is going to rise as it coming from B towards A is going to rise, become maximum, but again fall to 0, okay? And that is what I'm showing you here in the graph right now, okay? So what we say is that This one we call it positive half cycle of the AC. That's how you're going to talk. This cycle between the 0 and the 2 seconds. And between the 2 seconds and the 4 seconds, we call it negative half cycle. So we have two half cycles, right? Negative half cycle. If I ask you, what is the meaning of full cycle? Full cycle of an AC simply means this whole graph. See, I'm going to show you like this. This whole curve from here to here, right? Which looks like a wave, okay, already, right? We call it not full half cycle, sorry. We call it full cycle of an AC. In this full cycle of an AC, we have a positive half cycle where it means current is flowing from A to B. We have a negative half cycle inside this full half cycle, right? Which means the current is flowing from B towards A. Again, I will tell you what's going to happen, right? If I continue the time axis, right? That means if I let the current flow again and again, right? You'll again notice that we'll get a full half cycle, not full half cycle, positive half cycle. Again, we are going to get negative half cycle. Again, get a positive half cycle. Again, get a negative half cycle. So this is going to continue throughout. Okay. So this is how we are going to represent our AC. Now let me tell you why it is like a curve. Okay. I'll give you an example. I think you can make it out. But I think, guys, you are clear at least what is an AC, okay? How to represent AC in a graph. Are you clear with that? So I need to ask you something, then I'll proceed, okay? Are you clear with the graph? Guys. At least the meaning of the graph. It is over here. You can check. Yes. I'm not getting any response, guys. Still waiting. I'm still waiting, guys. Hello. Are you clear, guys? Are you clear? If you're clear, then I'll proceed. No response. Can you hear me?
Yes, sir.
Not so clear. Okay, not so clear. Okay, look at the graph. Malem, okay, saying not so clear. Okay, look at the graph, and this is the current time graph, right? So this is the time 0. Here the time is 1 second. Here the time is 2 seconds. Here the time is 3 seconds. Here the time is 4 seconds. So basically, I'm telling you what is the meaning of this graph. Is the current constant? No, the current is definitely not constant. When the time is 1 second, the current is 5 amperes. Just an example. It has reached 5 amperes, right? It's rising. See, current here has 1 ampere, maybe here it is 2 ampere, 3 ampere, 4 ampere, like that, right? But here at 1 second, the current is 5 amperes. But again, after that, the current is decreasing. I'm telling you that, okay? Right now, I'm not telling you why it is decreasing. I'm just telling you, suppose if we have such a current, right, which is increasing and again decreasing, right? Then I'm saying that the current is also changing the direction. Okay, so this one is -5. I'm going to call it still a current, but I'm going to call it -4, -3, -2, -1, 0, -4, -3, -2, -1, 0, right? So these are the values of current. The blue lines right now, if they're longer, right, they're showing me that there are more current. There's no blue line here because there is zero current there. No, that is what we are talking. Okay. So Malem, we call this one as positive half cycle, and this one we call it negative half cycle of the AC. Positive half cycle simply means, suppose if the current is going from A to B, flowing from A to B, negative half cycle simply means the current is going from B towards A. That's it. That's the meaning of this one. Okay. So in how much time full cycle is completed? The full cycle is completed in a time of 4 seconds. We call it time period of an AC. Okay, so time period of an AC right now is how many seconds for us? 4 seconds. Right now, please remember that. That is what is happening. Time period of an AC. A full cycle takes place in 4 seconds right now. Okay, it will be different for, of course, a different AC. Right now, I'm saying in this example, it is 4 seconds. Okay, Malem, is it clear? Little bit at least. Don't worry, things are going to become clearer and clearer slowly. Okay. Okay, I'll just ask you now something, okay? Look at this graph and tell me, if 4 seconds is the time period, time taken to complete both the half cycles, right? 4 seconds. What is the time after which polarity changes? The time after which polarity changes is capital T by 2, right? That is your 2 seconds. You can check 2 seconds later right now, the polarity is changing because the current is changing the direction, right? We call it capital T by 2, right? Half of the time period, okay? If I also ask you right now, tell me when does the current becomes maximum? What is your answer? Your answer is the current becomes maximum at what time? 1 second. But will I call it 1 second or can I call it T by 4 seconds? Check. In general, I can call it what time? T by 4 seconds. Can you understand?
T by
Because
2.
T by 4, yes, because check. This is a full cycle. The time here is called capital T. The time here will be called capital T by 2. The time here will be called capital T by 4 because it's 1/4, right? 1/4, 1/4, 1/4, 1/4, right? I'm going to get the 4 times of 1/4. I'm going to get the full time, no? Okay, I hope you understand. This time here, let's be very clear with that, okay? How much time is this time? Anybody who can tell me? From here to here. Okay, let me show you one more graph very quickly. Time graph, okay? Small t, this is 0. I'm telling you from here to here is capital T, and I'm dividing into 4 parts. How much time are we talking here? This is definitely a time of T by 2, right? Half of the time period. What is this? Is it half of the time period or half of the time period? Okay, so this is, yeah, this one is then, this, what will be this much? How much is this time? Check. This is T by 4, this is T by 4, this also will be another T by 4. That means the time here will be 3 times of T by 4. I hope you got me. How am I setting up or putting up the time there? Okay, so I think you got me. Okay, when I give you this example, I think it should be clear. So this is 3 times of T by 4. Now, if I look at the graph and ask you, right, when does the current becomes maximum? You have to say the current becomes maximum in the positive half cycle after a time of T by 4. The current becomes maximum in the negative half cycle after time of 3 times of T by 4. I think this part is okay. I think you're okay with this. Okay. So I think we can proceed, right, guys? With the timing, things are clear, right? When does it become maximum? When does it become minimum? I think you're okay with that. Okay. Now let's go back to our this diagram here. So if I'm taking the first full cycle, right? It completed in capital T time. If you look at this now, right, it's a continuation of the same thing. Now it is taking how much time? 2 times, right? 2t, 2 times of capital T. So this represents twice of the time period. That means we have 2 full cycles. This is one full cycle. This is one full cycle being completed in a time of capital twice t. Okay. Okay. Let me ask you again. Okay. One simple question. Can I say that? Can I say? Okay. Just think about it and tell me the value of the current. What do you think? Is it constant or changing? That's the first question. What do you observe here? Is the value of the current constant or it is changing? A simple question. Guys.
Changing.
Changing. Yes, current is
Current
changing.
changing.
Of course, it is changing. It is starting from 0, it is becoming maximum, again becoming 0. Then flows in the opposite direction, becomes maximum in the opposite direction, again becomes 0. Current is changing. It's changing with time, right? Do you agree on this or not? Yes. If you ask me, I can tell you the current at any time. Okay. Example, if I ask you, okay, this is 1 second, this is 2 second, this is 3 second, this is 4 second, this is 5 second, 6 second, right? If I ask you what is the current at 5 second, you will tell me, yeah, this much is the currency, this much, right? How much up it is in this graph, right? Okay, how much is the height of this graph right now? That is the value of current, right? Right now it is I naught. Let me say 5 amperes for the timing. Okay, so this is 5 amperes, that is also 5 amperes. If I ask you what is the current, okay, after 6.1 seconds, just an example, this is 6 second mark, this will be 6.1 second mark, this much is the currency. So at different time we have different current. Okay, so that's what I'm going to write now. See, current is a function of time. That means, okay, yeah, so that means at different timings we are going to get different current. That is the meaning of current is a function of time. Current depends on time. Okay, now let me ask you and write down something and tell me whether you agree or not. Okay, so I'm going to do that very quickly. Just check. This thing is going to be useful in your wave optics also. Okay, I'm drawing sine x. You know what is sine x? And this is x. This is our 0 mark. Everybody knows the behavior of sine x, I think, no, by now, right? Okay, I'll give you some angles first. This is the angle I'm talking about is pi by 2. This angle I'm talking about is pi. This angle I'm talking about is 3 pi by 2. This angle I'm talking about is twice pi. Now, why have I drawn it like this? Let me quickly tell you. See, this value of x means they are angles right now. They are angles. If I ask you x is 0, what is the value of sine x? Sine x means sine 0, right? That is like the value of y, okay? These are the values of x and these are the values of y, no? Y coordinate is going to be 0. If x is 90 degree, sine 90 is how much? Is equal to 1, okay? If x is 3 pi by 2, or let's say not 3 pi, but let's say pi, 180 degree, sine pi is how much? 0. Finally, if I tell you x is equal to 2 pi, right? I'm going to try it here. Not 2 pi, sorry. 3 pi by 2. 3 pi by 2, okay? So sine 3 pi by 2, let me tell you, is minus 1. And finally, if I tell you x is equal to 2 pi, then I have to tell you the sine of 2 pi is again how much? Equal to 0, okay? So when I plot a graph, it's going to take up this shape. See, sine 0 is 0. Sine 90 is 1. The graph rises till 1 because sine 90 is 1. Sine pi is again 0. Sine 3 pi by 2 is minus 1. So we go up to minus 1. You can understand the graph, okay? And then finally, we have sine of 2 pi again becomes 0. So we are plotting a graph. And if you notice, right, it is exactly how I have drawn the AC earlier, okay? The value of the current not rising linearly, but in the form of a curve. And we have this curve right now, okay? So don't worry, you will understand the moment I start speaking. So you tell me, okay? Just think and tell me. Can I write current is equal to T? Is this correct or wrong? First question, very simple question. If I write current is equal to time, let me show you what kind of graph we are going to get. This is time, this is current. You're going to get a graph which looks like this. So you tell me, can I call it alternating current or cannot call it alternating current? Time is 0, current is 0, time is 1, current is 1, time is 2, current is 2, time is 3, current is 3, right? So this is not definitely the formula, right? How current is depending on time. This cannot be the formula, no chance. Because our graph has to fall back also, right? Our graph is rise also and fall also, okay? I equals to T or I equals to 5T or anything, right? It's not a graph for us. I even cannot have I equals to T square. Let me show you what kind of graph we are going to get. If I have a graph I equals to T square, the graph will look like this. So definitely not matching with our graph for alternating current, okay? But if I ask you, can the current look like sine of some T like this? Can the graph look like this or not? What do you think? I'm talking about the formula.
Yes,
Yeah, I'm talking about the formula
Yes,
between. Yeah, I'm talking about the formula between the current and the time, right? It cannot be this. That is what I told you. But our current can look like this. Yeah, this is quite okay, right? Because if I draw a sine curve, it looks like this. And if I talking about alternating current also, yeah, it looks like this. Okay, because they're almost same shape graph. Okay, so I'm going to write a formula right now directly. Then I'll show you the features, and then you tell me whether everything is fine or not. Okay. Suppose I tell you, see. Suppose I'm talking about an AC, and then I tell you the current in the AC, okay, is equal to 0 when the time is 0. Then I'm telling you that the current in the AC is 5 amperes when the time is 1 second. Current in the AC, I'm going to go do in detail, but let's do properly. No, that's what I told you. 0 amperes when the time is 2 seconds. Current in the AC is minus 5 amperes. You know the meaning of this one now, equals to 3 seconds later. Then I tell you the current in the AC is 0 amperes again when the time is 4 seconds. And in between, there are numbers which I'm not writing, but I'm going to plot this graph, okay? Okay. The first thing is, when I plot the graph, you already got an idea. This is time axis. This is current axis. 1 second, 2 second, 3 second, 4 second, right? Your graph is going to rise for 1 second, fall for 1 second, rise for the next 1 second, and then again fall for the next 1 second. Okay, so everybody's clear with this graph. I've drawn it earlier. Okay, let me just put the points here right now. 0, 1 second, 2 second, 3 second, 4 second. You know, this is positive half cycle, negative half cycle. You know the meaning right now. I'm writing here I maximum value, right? That's the maximum value of the current, and the maximum I see right now is 5 amperes. Okay. Okay, I'm going to do something now. Check. Okay. All of you will agree with me that this is called capital T. Right now in our picture, our capital T looks like 4 seconds. Everybody will agree with me on that. Okay. Now, can I tell you that anything which has time period, right? Time period basically means time to complete one full oscillation. You can say it is like an oscillation of the whole current only, right? Oscillation means going to the right and coming back to the left, right? If a pendulum goes to the right, again comes back and reaches the same position, we call it one oscillation, right? Okay. So we have this to and fro motion right now in our current also, so we can compare it to oscillation or periodic motion, right? That's why we have a time period. So anything which has a time period, I can calculate the frequency also, okay? So I'm just going to do that and ask you. If I ask you what is the frequency, your answer is reverse or inverse of time period is called frequency. So I'm going to get 1 by 4 seconds. That is like 0.25 hertz. Okay. That means there are 0.25 oscillations in 1 seconds. And you can understand, right? This is a 25% of the oscillation in 1 second. Okay. Right? It's the not the whole oscillation, right? In 1 second, you are getting full oscillation? No. You are getting 25% of the oscillation. That's why we get 0.25 as the number. Okay. For the time being, I'm doing that. Later I'll show you a much better number, but no problem, don't worry, we have calculated the frequency. Okay, now there's something I'm going to bring and just check whether you understand or not. Okay, once I can calculate the frequency in talking about periodic motion, we can also define something called angular frequency. The formula is take the 2 pi and multiply with f, right? So you get angular frequency. The way to do is that simply take 2 pi and multiply with frequency, that is 0.25. No, the units of this is radians per second. Okay, radians per second. You are not allowed to write pi equals to 180 degree. Okay, you cannot do that. This is a radian measurement. You have to write pi equals to how much? 22 by 7. Please remember that. Okay. Okay, so when I substitute, I'm going to get in radians per second. Please remember that. But don't worry, we have got a omega value. Now you must be thinking what is going on. Okay, so just let me just show you now. If I write I equals to I naught sine omega t, let me tell you how this equation is going to be handling all the values of the current. Okay, let me tell you one by one what are these, then I think I can proceed. Okay, just check. If you have any doubts, you can ask me. So let me just put it over here. Okay, check now. See, first of all, let me tell you what am I doing. This I for us represents current. To be more accurate, it represents instantaneous current. That means you ask me or tell me this t here represents instantaneous time. Okay, instant of time. Don't worry, you'll get me what I'm trying to say. Suppose I write I equals to I naught. I'll tell you what is I naught also. Give me 1 second. And suppose if I write here 5 seconds, check what have I done. Okay, in place of this t, right, I've written here 5 seconds. That simply means I want to know what is the value of the current when the time is 5 seconds. Simply if I write I equals to I naught, and this equation is going to help us. Okay, I'm going to show you, then we are going to start using it. Okay, if I write here 10 seconds, right, it simply means I'm trying to find using this formula what is the value of current at 10 seconds, not after 10 seconds, but let's say at 10 seconds. It is not instant average current. Okay, it is instantaneous current. Okay, now you must be thinking why omega is appearing here. Okay, now let me just give you a short reason for why omega should be there. Okay, check. Sine, I wrote omega t. We all know inside this sine, right, only angle can enter. You cannot write time. You cannot write sine t. If I write somebody write sine t, okay, it's wrong. Why? Because t is time here. Sine cannot take time. Okay, sine has to take an angle. Now let me tell you what is the best part. The best part is if I write sine, omega is like angular frequency. The unit of angular frequency is radians per second. That is omega unit. Okay, then I have this t with omega, right? So into seconds again. This seconds and second gets cancelled. This is omega units, this is time units, and you simply get radians, which is the unit of angle, and sine is satisfied with that. Okay, because the unit you're getting is radians. No, that's why we simply write sine of omega t. We cannot write just sine t. It doesn't happen like that. Okay, so please remember that's one reason I showed you just now. But don't worry, you will get me now what is going on. See, now one more thing. If I write I equals to sine omega t also, okay, this is not going to be correct, because if I draw a graph which looks like that, it's simply going to rise and fall to +1 and -1, +1 and -1. If I write 2 in front of sine omega t, right, twice omega t, it simply means the graph will rise up to 2 and fall to 2 and again become 0. I hope you understand the meaning of this 2, right? We call it amplitude also. Okay, whatever is in front of sine, right, we call it amplitude. Okay, so now just check and tell me, all of you, okay, for this graph right now, if I want to write I formula, right, will the I formula look like this or not? That's the first question. I'm trying to represent this whole graph by an equation, right? Because every graph has an equation. Okay, so you have to tell me, am I going to put here nothing, or I have to put something here according to this graph? Look at the graph. How much it is rising? It is rising to 5 amperes. It's falling to minus 5 amperes. That means I must write here 5. Please remember that. Okay, 5 amperes. If I do not write that, the graph means it's going to rise to only 1 amperes. Okay, but obviously right now it is going to rise to 5 amperes. I'm going to write here 5. This 5, we call it peak value. Please remember that. We call it peak value of AC. Guys, are you clear what is peak value of AC? At least peak value of AC is clear. Is it clear? Don't worry, we'll go to omega t thing also. Okay, give me some time. Okay, maybe you're not getting me everything, but I think slowly you will understand what is going on. Okay, now let me tell you what does the omega part does here. Omega, don't forget, it was frequency. See, if I draw a graph here, looks like this, right? Okay, let me just compare to, this is graph number 1. Let me just show you another graph. Okay, let me just draw with red. Next graph. Look at the number 2 graph, the red graph, and tell me what is the difference between the first graph and the second graph, or what is the similarity between the first graph and the second graph. Are both the graphs rising to same value or not? Do they have same amplitude or different amplitude? They have same amplitude, but look at the time. Okay, who has more time period and who has less time period? The first graph has a time period of capital T. Right now it looks like that, maybe example 4 seconds, but the second graph is completing, right? The second graph is having a time period which is not 4 seconds, but it is only 2 seconds, right? The second graph is completing much faster. Okay, so just now I compared this and this. See, I have a graph which looks like this, then I told you I have another graph which looks like this. I'm not drawing properly, but I think you got me. Okay, the first graph, second graph right now. Okay, let's check. Second graph has a time period of 4 seconds. The first graph has a time period of 2 seconds. If I ask you what is the difference, you're going to say frequency, right? Which graph has smaller frequency? First one or second one? Check. Smaller frequency and higher frequency. Which graph has higher frequency? Yes, some answers. Then I think we will proceed. Frequency, if you remember, inverse of time period, right? Time period. The second graph right now, the red one, okay, has a bigger time period. That means the frequency of this graph will be less, or this AC will be less. The green graph has taking less time, right? Less time to complete the oscillations. So frequency of this will be more. Okay, so first graph right now, according to this, has more frequency, and the second graph has less frequency. Okay, frequency means how often or how quickly the oscillations are taking place. Okay, so that is what we are dealing with right now. Okay, now let me just show you. See, if I write sine of twice t, and if I write sine of t, right? Okay, 1t. Let me say I've adjusted with omega. Okay, it simply means number 1, number 2. This one, right, where I'm writing twice t, represents more frequency. This one where I'm writing only 1t represents smaller frequency. Okay, that means for this one, the graph is this one. It's a bigger graph. Okay, means taking a lot of time because it has smaller frequency. But look at this. This is a much faster graph, or let's say this is a much faster oscillation of the AC, and it is represented by the smaller graph. Okay, smaller in terms of timing, right? So I hope you understand the meaning of putting sine of thrice t, sine of 4 times t, right? So, okay, this means much faster graph. Its frequency is large, frequency is small. Okay, you can also understand like that. I hope you got me what I'm trying to say. So now let me just show you what I was talking about, and I think you will be clear now. Okay, so where was I? I was talking about this graph, yes. Okay, so now check. Let me just remove everything from the picture here. Now you will get me what I'm trying to say. See, if I'm writing now I equals to I naught, sine omega t. Let's start putting the values, okay? For this particular graph that I'm drawing, I told you the amplitude, the maximum value is 5 amperes. I'm writing here 5 amperes. The peak value I told you of the AC, every AC is going to have a peak value. Sine of omega. Right now I have calculated the omega, you check. I got the time period by looking at this graph. Frequency I've calculated the omega, which is this much. So let me just do it very quickly. I'm going to write here 2 pi into 0.25 right now, okay? I've written that omega value. I'm going to multiply with time. I'm going to put it like that, okay? So see, I'm getting an equation where I simply have to put, I know the omega and the frequency and time period, okay? I simply have to put this time, and when I put this time, I'm going to get the current at that time. Let's do it, okay? Let's do it right now, very quickly, okay? So see, looking at the graph, guys, if you check, if I ask you, what is the current? What is the current at 4 seconds? Everyone very easily can tell me, right? The current at 4 seconds is equal to how much? 0. That is by looking at the graph, okay? Now check. I'm going to do the same thing, okay? I'm going to tell you right now that the current at 4 seconds is equal to 0 by using this equation that I formed for this graph. By looking at the graph, we have formed this equation, okay? So I'm going to do that right now, see. So I'm going to write I equals to 5 amperes sine 2 pi into 0.25 into t. This t right now is 4 seconds. So I'm writing 4 seconds, see, for this t. The moment I put here 4 seconds, you understand, right? I'm finding the current at 4 seconds, not by looking at the graph, but by using this equation. So check what we are going to get, okay? 4 into how much is this? 0.25 is 1. 1 into 2 pi is 2 pi. So I'm going to get I equals to 5 amperes of sine of 2 pi. Everybody knows sine of 2 pi is 0. 0 into 5 amperes is 0 amperes. And if you come back to this graph, at 4 seconds, I saw that the current is how much? Current is 0. Can you understand? And I know that right now by using this equation, okay? Now I'm going to call it the name, okay? We call it instantaneous current, okay? That is the name of this current, and we can find it. So let me just quickly form another equation very quickly for you, and I think you will understand what is going on very quickly, okay? If you understand this graph now, I am done, okay? Talking about this. Okay. If I tell you this is current, this is time, right? All of you can understand right now. I'm trying to represent a current, which is, we call it alternating current. We're trying to represent AC. If I ask you what is this, I can tell you the current is flowing from A to B, current is flowing from B to A. Fine, no problem with that. These are timings. This is 0. This is, if you break the times, this will be 2 seconds. This will be 4 second mark. This will be 6 second marks, and this is 8 second mark. Okay. Okay. All of you guys now look and tell me, if I tell you this is the highest value of current is, let's say, 10 amperes. Guys, you have to form an equation now for me. That's it. I equals to how much? What is the maximum value for this current right now? This AC. It's a different AC, okay? What is the maximum value? Because I need to start putting, right? The general equation is I naught sine omega t. Later you can change it also. Right now I'm not changing. I can show you for cos also, but I'm not going to do that right now. I'm going to work with sine, okay? Guys, please tell me how the equation is going to look like. In place of I naught, right? I'm going to write how much, guys? Yes, hurry up, some response.
Sir, 10 amperes.
10 amperes, okay, 10 amperes, because there's a maximum, okay. Sine, I'm going to write sine. Let me tell you why I'm writing sine, okay. Anything which starts from 0, right? A curve which looks like that, if it's starting from 0, it should be sine curve. If a curve starting, okay, if a curve is starting from some maximum becoming 0 and like this, right? This is also continuation, no? See, this is also a curve. This is cosine curve, okay. Because cos of 0 is how much? Cos of 0 is 1. So it's going to start from maximum, no? So that is cosine, but this is sine. Okay. In place of omega, tell me, what do I write? Omega, in place of omega. Yes, yes. Where is our hero? Our hero is not
Sir,
here.
2 pi.
2 pi, very good. I'm going to write
2
here 2
pi.
pi. Yes. Then in place of omega, only 2 pi, or should I write f also? F, right? I'm going to write here small t. Let's just proceed and simplify much further. I'm going to write here 10 amperes sine of 2 pi by capital T, because frequency is 1 by T. Okay, so I'm using that, you can understand. To be much more accurate, I'm going to write 10A, right, amperes sine of 2 pi. If you ask me what is the time period, right, your answer is the time period or time taken to complete one oscillation is how much? 8 seconds. So I'm going to write here 8, and then I'm going to write small t. So this is our equation, okay? That is what we have formed right now. An equation that is going to represent our alternating current, okay? I'll just quickly give an example. Very quickly we'll do that. Let's calculate at time t equal to 6 seconds. What happens? Not by looking at the graph. By looking at the graph, I think you can easily tell me, right? 6 seconds time, the current is how much? Minus 10 amperes. And you understand the meaning, right? The current at the 6-second mark is flowing from B to A, and right now it is maximum with the value of 10 amperes. That means I can tell you the current and time, right? Current at any time, okay? So let's calculate using this equation now. Say, at 6 seconds, I'm going to use it like this. I will be equal to, you have to write 10 amperes, you have to write sine, you have to write 2 pi by 8, which is the capital T, into 6 seconds. If I start cancelling, right, I'm going to get like this, say, this 2 and this 1 gets 4. This is going to get me 2, and this I'm going to get 3, right? So I'm going to get I equals to 10 amperes, and I'm going to get sine of 3 by 2 pi, or 3 pi by 2, okay? Sine of 3 by pi by 2, everybody knows it is equal to minus 1. So I'm going to get 10 amperes times of minus 1. So I will be equal to minus 10 amperes, right? And all of you will agree, right? At the end of 6 seconds, or let's say at 6 seconds, the current is minus 10 amperes, right? So do you understand what we have done just now, all of you? Are you clear? Are you clear, guys? What am I showing you, and are you getting me? At least a little bit of it should be fine. You don't have to understand everything right now. Yes, Pratyusha is there. I'm going to wait for your response. Pratyusha, is it okay? Okay, fine for Pratyusha. What about Beauty? Beauty, is it making sense? Freddy wants to talk. Yes, you can talk. Okay, Beauty is fine. Bhageshri is also here today. Bhageshri, are you clear what I'm doing?
Yes, sir.
Okay, then Denzel is here.
Yes, sir.
Okay, Rahul Badmas is also here. Rahul. Okay, Rahul doesn't want to talk. Okay, fine, then I'll proceed. Okay. So after doing so much, okay, that is what I've just done. See, let's be clear with the terms and everything, and then I'll proceed. Okay, so see, so you can either represent by a sine function, that is what I showed you just now, or you can even represent by a cosine function. When will I use cosine function? If my graph is rising from some value and then becoming less and more and less and more, something like that. Okay. Somebody is calling me. Just give me 1 second. Yes. Hello. Hello. Yes. Oh, Surajit, na? Acha, sir. This is your number, na? Okay. I'll do like this. I'll by 11 you just be ready. Okay, before 11. Okay. Before 11 you just be ready. I'll give you a call before I reach a health complex, huh? Okay. I'll save your number. Yes. Okay. You can also call me tomorrow morning, huh? Yes. Okay. Okay, so what was I saying? Yeah, cosine function, you understand. When am I going to write? Let me just tell you quickly what is what. Please remember, don't just call it current, okay? We call it instantaneous value. That means value of AC at any time. We have to mention the time. The moment I say I, you have to mention the what time, right? I naught represents the peak value, the maximum value of the AC. We are going to use like that. Omega represents angular frequency of the AC. Angular frequency very high, no? Means simply frequency very high. Frequency very high means the AC, right? The current which is going back and forth is doing that very quickly. That's the meaning of frequency. It's doing very often, okay? Going left and right, very often. That's the meaning of omega and F, okay? And small t represents any time that I want to talk about. I can talk about 5 seconds, 10 seconds, 100 seconds later also, okay? And what I've shown you right now is this. You can draw the graph and tell me the value of current at any time, or you can simply write this equation and calculate the value of current at any time. Okay, so this is current time relation, and that is what I've told you just now. Okay, I think you got me what I'm trying to say. Then yes, we are going to do something now. Okay, check all of you. This derivation is there. I do not know whether it's a good time or not, but let's talk about something called average current first. Right? Then I think I should do this first. Okay, today I'm not going to get full time. Let me do like this. Let me see tomorrow, guys. Is it okay if I meet you guys tomorrow? Now, why am I saying tomorrow? I'll tell you. Because Monday, I think I don't want to take on Monday. Okay, maybe I'll take on Tuesday. But is it okay if I miss the Monday class and take tomorrow? Saturday. Time, I can keep it same time, 7:30 to 9, like that. If you're okay with that. Okay, we'll talk in the group. Okay, if anybody has problem, we'll change. Okay, maybe I can still take tomorrow. I mean, so I'll take tomorrow, but maybe I can take Monday also. Let's see. Okay, okay. So please, please bear with my timings. Okay, sometimes I'm calling you Saturday, Friday, like that. No, so this is now high time for you to start preparing. Okay, don't take it lightly. I'm telling you, huh? Okay, Rahul is okay with that. Very good. Okay, so only few students have joined these days. Okay, I don't know what about others. Okay, because yeah, some of them they still have exam, I think, right? Okay, whatever it is. Okay, I will just teach you for another 5 minutes, maybe not more than that right now. Okay, but try to get this idea. Okay, something very nice is going to happen. See, so I'm taking this as time axis. This is the zero. This is the positive current. Everybody knows this is the negative current. And once I start drawing a graph which looks like this, okay, everybody's clear what I'm doing. Okay, that means I'm trying to represent AC, the current which goes back and forth. At what time and all, we all have all the information. How much is the maximum current? We have the information. Okay, I know. Okay, let's just put some numbers. Okay, let's check. See, if I want to now talk about this, let's just draw a circuit. I have a bulb. Okay, I have a bulb, and then I have a, sorry, wrong source. I'm going to draw an AC source. I have to say now, right? Okay, I can tell you now. This is a bulb. If I ask you now, you know, right? The current flows from A to B, the current flows from B to A, right? But depends on timings, of course. If for the 2 seconds current flows from A to B, for the next 2 seconds current will flow from B to A, and the total time period is 4 seconds. We know that. Okay. Okay. If I ask you now, what are the values of the current for 2 seconds? See what are the values you are going to tell me. Okay. Let's say this is 10 amperes, just an example, peak current. So see, this is your plus 1 ampere, plus 2, plus 3, plus 4, plus 5, plus 6, plus 7, right? We are going to have all those values. Even we are going to have till 10, okay, plus 10. All these are also up to 10 values. All these currents that I'm drawing right now, they're positive values, right? And if I ask you what is this, these are all values of the current which are negative currents, no? Okay, that is what is going on, okay? Now if I ask you, what is the average current? What is the average current that is passing through this bulb? Okay, your answer will be like this. See, I have to write all the values of current for all the timings for both positive half cycle and negative half cycle, and have to divide by how many of them we have taken. No, let's say we have taken n number of currents. Okay, now all these are currents. Okay, that's why I'm taking n number of currents. See, all these are very, very different values of current, right from zero time to capital time. I'm talking about one full cycle. How much answer do you think I'm going to get for average current? How much do you think I'm going to get answer? Anybody who can give me an answer? How much average current do you think is passing from the bulb? I'm talking about average of an AC, okay? Average current or average value of the AC. Why we are calculating AC average? It's because this AC current that we're talking about doesn't have a same value, right? It changes from 0 to I naught, then falls back again from 0 to minus I naught, falls back to 0, right? It has different values of current. So I can calculate the average, right? Just like you're getting different marks in different subjects, you calculate average. So here also we want to know what's the average current passing from this bulb or average AC current, okay? What's your answer? It should be simple, guys, very simple. What's the answer? Yes. Anybody with some answers? Or anybody who knows the answer? This is done in your school by now. How can you not tell me what is the answer? You don't learn anything in the school. Okay, school though you're not going only. Yeah, maybe if you have gone to school, maybe you would have give me properly, very quickly. Still, you have brain. Even if you don't go to school, you have brain. You should be able to tell me what's the answer. Yes. How much will be the average current? Nobody is telling me. The average current is how much? Does it ring a bell now? The average current is 0. Why did I write 0? Because see, if I write this current 1, if I write this current as plus 2, if I write this current as plus 3, plus 4, so on, plus 10, right? Plus again, so on values, right? On this negative half cycle, I'm going to get the corresponding negative values, minus 1, minus 2, minus 3 divided by n. And no matter how much you take, right? You're going to answer equal to how much? 0. Can you understand that the average current is going to be 0? Half of the current are positive and half of the currents are what? Has negative values, right? Can you understand that the average current is 0 in an AC? Yes, some response, guys, then I can proceed. Yes.
Yes, sir.
Okay, Freddy is saying yes. What about others? 1, 2 more responses very quickly, guys. Okay,
Yes,
Malan is
sir.
saying yes. Okay, fine. Rahul is also clear with that. So average value is 0. I'll show you another way. See, what do you think? How much charge is transferred? Current means there's a transfer of charge. In this full cycle, okay, in this full cycle, what do you think is the average transfer of charge? From A to B or from B to A, what's the average transfer of charge? What do you think? Yes. Transfer of charge will also be equal to how much? 0 for the full cycle, okay? Because if the current is going from A to B, electrons are getting transferred from B to A. That happens for half cycle, positive half cycle. When I add up the negative half cycle, right? If I'm talking about the negative half cycle, current goes from B to A, and whatever charge has been sent from B to E, right? Whatever number of electrons has been sent from B to A, same amount of electrons will be sent back from A to B. So now if I ask you, what is the total transfer of charge? Your answer is how much again? Your total transfer of charge is 0 again. Okay, so I hope you understand till here. So this is not the way you should take the average. Not proper. Okay, this we cannot do. Not proper way to take average, because you're going to get 0. And you will notice the bulb will glow or not. What do you think? Average current is 0. Okay, average charge transferred is 0. But my question is, will this bulb glow or not? That's the question. Then we'll stop. Okay. Yes, guys, hurry up.
No, sir.
The bulb will not glow, right? Rahul is saying no. What about others? Yes. Quickly, guys, I'm also hungry. I want to have something before I start class 11 tuitions. My question is, will the bulb glow or not? Or by the way, do you know why the bulb glows when the current flows? Why the bulb glows? Whenever the electrons, they move through the bulb, current means electrons, right? They make the bulb hotter and hotter, right? Hotter and hotter. Whenever the filament present in the bulb becomes hot, it emits light. That's the picture, right? So my question is the bulb going to glow if the average current is 0? Will the bulb glow or not if the average current is 0? Yes, guys. No idea, or what is the thing? Somebody said bulb will not glow. I think Rahul said bulb will not glow. Think about this, okay? For 2 seconds, the electrons are going from B to A. When the electrons, they go from B to A, they are going to produce heat in the filament and the bulb will glow. For the next 2 seconds, the electrons will change their direction, go from A to B like this. But still they are going to flow from the filament and they're still going to make the filament hot. It does not matter whether the electrons are going from left to right or right to left. The electrons will still flow from the filament of the bulb and still they are going to carry energy. Doesn't matter left to right or right to left. Still the bulb is going to become hotter and the bulb is going to glow. Okay, that means even though the average current looks like 0, right? The positive current and the negative current, even though the average transfer of charge is how much? 0. Even though then, right, there is electricity that we get, right? Okay, we get the light being switch on. Okay, the current is going to be switch on. Okay, for positive half cycle and even for your negative half cycle. Okay, so tomorrow I will talk about, this is not the correct way to find average current. Still there is a method, okay, to find average current, and I'll show you that tomorrow, guys. Okay, that means there's a way, we do not call it average current, by the way. We have a totally different name. Let me just remind you. Okay, if you have seen in the school, we call it IRMS. This is the best possible way of knowing how good our AC is. Okay, average current is not the good way to find how good our AC is. Okay, it's not the good way because you're going to get zero. But we have something called IRMS. We call it IRMS of this AC, or IRMS of this AC, or IRMS of this AC, and that's how you are going to check the quality of the AC. Okay, that means how much current is actually being transferred or something like that. Okay, we are going to talk about tomorrow. Okay, guys, for today I think I made it clear. Actually, at least I made it clear what is this, right? Is it okay? For today I think I will stop. Is it okay, guys? Just say yes or no, then I will stop. Anybody who has doubts still can talk to me.
Yes, sir.
Okay, Rahul is fine with this part at least. Yes, guys. Rishita is there, can talk. Freddy, Freddy is always used to respond.
Yes,
Fine.
sir.
Okay, Sushant. Okay, Rishita is fine. Okay, let's do like this. Hopefully, I'll try to meet tomorrow, guys, huh? Because it will be fresh and all. By tomorrow, I think we'll be doing it fine. Okay. So bye, guys, huh? I'll stop. Bye.
Bye, sir.